So I want to continue on our discussion of PCA. I wanted to cover it last week, last class itself, but there was one part that I wanted to demonstrate that I didn't get a chance to. So let's sort of go into that. So remember last time we were talking about PCA, right? Principal component analysis. And the way we sort of talked about PCA was a tool, essentially, to reduce the dimensionality of the data, right? So if you have data in very high dimensional space, and you want to work with smaller dimensional data, then PCA is one way to do that. And we saw how it works, right? So you essentially center the data, you compute the eigenvalues, and then you take the eigenvalues that correspond to the highest eigenvectors, and we analyze that, if you do that, then what you're ensuring is that you are going to capture the most variance that you can using that many dimensions. So you can take any other way to compute lower dimensionality of a data using linear combinations, of course, right? And PCA will always give you the best answer. And we saw that using this classical PCA theorem, which says that if you take any L basis vectors, right? So PCA also kind of takes L basis vectors that it multiplies with your original data to get reduced space, right? If you use those L basis vectors to recover your data, then the error between your original data and your observed or recovered data will be the minimum if you do PCA, right? So that kind of helps us in saying, okay, we should use PCA essentially, right? So that is the idea, and now I want to show you how it is useful, right? So we would sort of look at a couple of examples here. All right. And let me make it bigger. So this is our PCA workbook, right? And we looked at all these simple examples, and I was looking at this hand digit recognition, hand digit data, written data, or handwritten digit data, right? Which we have seen in your programming assignments, right? The first thing I did was I took all the 3 images, right? And this is just one of those 3 images. And then I flattened it so that it is a vector of 784 length. And then I ran PCA on it, right? And then what I did was I said, I'm going to represent my data using only one basis vector, which means that I'm reducing the dimensionality of my data from 784 to 1, right? And then we said, let's try to recover our image. So using that formula over here, which is, I know my W has only one vector, Z has only one value now because you have reduced the dimensionality into one value. So when I multiply this vector with this value, I can recover my image, right? And of course, there will be an information loss. This is not a lossless compression, or lossless approximation. So what you will see is that this was your original. So I'm just plotting one of the images. So this was your original image, and this is what you recover. And this is the error between these two, right? So of course, since we have only used one principal component, and so clearly we have lost a lot of information, but you still see that, you recover something that's close to 3, right? So it's not that bad. In fact, I would sort of suggest that you can go back and sort of do this for your data, right? Reduce all of your hand digit data into one dimension and try to run your neural network or logistic regression on this. And you will see that it won't do that bad because the images that you're getting are not too different from the original image. So for the purpose of analysis, so if you want to use this reduced data for building a classifier, this might be good enough. For the purpose, if you want to use it for image like compression, like what JPEG does, right, then this is not a very good idea because it loses a lot of visual quality, right? So if you do JPEG compression on this original image, you will reduce the size, but you will sort of, it gives you a good sort of visual, right? So JPEG, because it does, its purpose is not to sort of maintain the variance or maximize the variance or anything like that. Its purpose is solely to have as less loss of information as possible. PCA does something else, but if you use this data for analysis, this would be reasonable, right? And then, of course, this is a pretty drastic case where I'm saying I only want to use one principal component, but you can sort of try larger numbers. I think we did that last time. And then you'll see that, okay, you are slowly getting closer to the original image and so on, right? So that is the idea. So now what I want to, so in this experiment, what I did was I only took 3-digit images, right? What if I take all of my images together? So here I'm loading all of my data into this all train data, all right? I'm going to scale it, because remember, for PCA you want to scale it first, make it mean 0, and then I run PCA on this with L. Now right now I'm using all of my principal components because I want to see the scree plot, right? So this is how the scree plot looks like. So what this tells you is that if you use only the first principal component, then this is sort of the loss that you would incur, how much information or how much variance will not be captured by just the first component. And as you include more and more principal components, you will sort of cover, or you will explain more and more variance, right? So that's the idea. But what you see interestingly here is that after 100, you don't see much improvement, which means that you could have reduced the dimensionality to 100, and if you run your logistic regression or neural network on this 100-dimensional data, you'll pretty much get as good results as you got for the full data. In fact, it might even give you better results, because later what we will see is that there are all these dimensions, right? But all these dimensions are so correlated with each other that they might actually confuse your classifier, right? By only looking at these 100 clean dimensions which are orthogonal to each other, it might give you better results, right? However, in any other data set, if you see, instead of this scree plot, if you see more of a linear decline, right, then PCA won't help, because what that plot will tell you is that there is no small dimensionality, no true dimensionality of the data. The data is what it is, so you have to use the whole thing. But typically in most real applications, people tend to use PCA because oftentimes when you have very large number of variables or features, it's not like all of them are useful, right? This helps you delete those. So here's what I did. So I want to use PCA for visualization here. So what I did was I embedded my data using first three principal components. So basically every image will now be represented by 3 numbers, right? So first, second, third. And then if you draw a 3D scatter plot of that, this is what you get, right? So essentially this is all of your digits. So every dot here is one of your digit image, okay? And they are colored by their digit number, right? So so what you'll see is that all the blues are here, which are digit 0. Digit 1 kind of forms its own sort of a cluster, and that is sort of intuitive, because it's not the variation in 1 is not that much. If you look at the actual data set, there are not too many ways in which you can write a 1, right? That's why 1 kind of happens here. But some of the other digits, like let's say 8, right, or 5, they kind of are all over the place because there's a lot of variability there, right? So this is one way of using PCA. Of course, it doesn't do a very good job in separating these because I'm only using first 3 components, whereas for what this scree plot tells me is that you need to use at least 100, but of course I can't visualize 100, right? I can also do like a 2-dimensional PCA, and then all of these things go into a 2-dimensional vector or 2-dimensional space, right? And in fact, if I hover over it, it tells me what digit it is. So like these are all 9s, these are all 1s, right? So as you reduce your dimensionality, essentially what you're seeing is that the variance is getting smaller, right? Because you're losing more information. But these are some of the ways PCA is used, right, to look at the data when you have only 2 or 3 dimensions in which you can look things at. All right, so that is one thing. Any questions so far? Okay, so I'm going to show you one more application of using PCA for face recognition. So there was a paper, I don't know, very long time back, which is called eigenfaces. So essentially what they did was that they did something like what we did for images, for the handwritten digit images. Instead of the digits, they had faces, and then they ran PCA on it, right? So each principal component was called eigenface because it kind of captures some information about the face. I'll show you that thing. So this is the data that I have downloaded from it's called a Yale faces data set. It has essentially it has lots of images, right? And what they did was they took every test subject and they asked them to pose in different ways. So you see on the top the different sort of settings in which the images were taken. So center light, wearing glasses, happy face, left light, and so on. So I downloaded some of these data sets, and this is I've plotted some of them. So you'll see there's a whole lot of variation. So there are different people, of course, right? And then even for a same person, you have images under different conditions. So that's the data set. Then I run PCA on it, right? So I do all of this. So, okay, so the first thing we want to do, of course, is to center this data. It should have mean 0. So what I do is I create the mean vector for all the images, and if I reshape it, this is what it looks like. So this is all the images put together. That's the average face, right? And then I remove that average face from every image. So this is what the image looks like. It still looks pretty reasonable, right? Now what we do is, so in my training data, I only have 100 images, and their dimensionality is 77,000 because that's the, it was an image and then I flattened it out. So it's pretty large. Then I do PCA on this, right? So first thing I want to do is see how the scree plot looks. How does the variance sort of changes as I include more principal components. And you see similar thing as we saw in the handwritten digit thing, that by the time you use the top 20 components, that's good enough, right? After that you don't get much benefit. So that's the idea, right? And now what I can do is I can take each principal component, right? So remember, what is the principal component? It is the eigenvector of your covariance matrix, right? Your covariance matrix was D by D, which is 77,000 by 7,000. So the first eigenvector will also be a vector of length 77,000, right? And then I can reshape it, right? So if I reshape it, this is what it looks like. So if these are the first 50 eigenvectors, which are reshaped into the image size. So this is like, the basic, so think about it as the base signal. So this tells you the base signal in your image. So every image has this part. Then this is second eigenvector, third eigenvector, and so on. So in that paper, this is what they call eigenfaces, all right? So now what we can do is we can construct images by using some of these eigenfaces. So for example, let's take a test image. Let's say this is the person, this is a test image, right? So I've just reshaped it and I center it. So this is what the centered image looks like. So what I do now is that I take this image, right, and I embed it into, let's say, the first principal component. So that will actually give me one number, right? So that will be my z for this x. And then I recover my x hat using this formula, which is I re-multiply it with that first principal component, because in this case w will only have one vector. And then I see what that image looks like. So you can see that, okay, using only the first principal component, the image doesn't have much information, right? It doesn't quite look like what this person is. But as I include more and more principal components, slowly you will see that the image starts looking more and more like the test subject, right? So by the time I've reached 50 test images, you will see that this image looks fairly like this test image. So think about it this way, that this test image was a 77760 length vector, right? I, using PCA, actually just represented it using 50 numbers. And then when I multiplied it with my principal components, I can recover the image. So it gives you a huge compression, right? So instead of the whole image, you just store the 50 numbers, and then you store your W matrix, of course. And then you can recover these images using PCA, and that theorem tells you that you'll not do a very bad job. All right, any questions so far? Okay, very good. And then actually this is for my PhD student, but so PCA is what we call a linear dimensionality reduction, right? Because all your features are combined with your basis vectors in a dot product, right? So it's linear. But there are other ways to do this kind of dimensionality reduction, which we call nonlinear dimensionality reduction. And I'm not going to talk about it at all, but but this is sort of an output that you get using one of those nonlinear dimensionality reduction methods. So this is called isomap. So the effect is still the same. You have handwritten digits in this 784 dimensional space. You embed it into 2-dimensional space, and because this is a nonlinear dimensionality reduction, you see a little nicer sort of a layout. So the visualization is slightly nicer, but I'm not going to tell you how this works. So this is not part of the course. It's just since it was here. Okay, any questions so far? Okay, very nice. So let's sort of wrap up our PCA discussion, right? So we have seen, the idea behind that eigenfaces paper was that once you learn these eigenfaces, right? So once you took all of your data and you learned these eigenfaces, the 50 eigenfaces. Now if I give you a new face, it can tell you if it belongs to the data that was trained for this PCA or not. So there's a nice application of face recognition here. Okay, so let's move back. So remember, when we talked about PCA in last class, we talked about it more from the linear algebra perspective, right? So PCA can be thought of as finding some orthonormal transformation of our data, and we saw that using the eigenvectors we can do that, right? But if you remember from 2 classes back, I was talking about factor analysis, which is more of a probabilistic latent model, right? Latent variable model. And then I told you that you can think of PCA as a special case of factor analysis. So that if you go down that route, then that PCA is called probabilistic PCA. So just refresh your memory, right? So this was your factor analysis model, right? Where you said that your X is essentially WZ plus mu with some covariance matrix, right? So you can think of, you can relate it to PCA. Remember in PCA, you say that X is W times ZI, right? So here we have a probability distribution. So we're saying X is a random variable whose mean is WZI plus mu and some covariance matrix. So very similar, right? In probabilistic PCA, what we do is we force this psi matrix to be just a diagonal matrix with exactly same values, which is sigma square. We force this mu to be 0 actually, okay? And then we also force that W is an orthogonal matrix. So because factor analysis does not put any constraints on W like that, right? But for PCA, we want all of our basis vectors to be orthogonal to each other, because you're doing dimensionality reduction in a new space, right? So these basis vectors define your space, and you want all of your basis vectors to be perpendicular to each other, because that's the definition of a coordinate space, right? So then you can see that when you do this, you can get to something that's very similar to PCA. Now, what is the difference between these two? The difference is that if you want to do PCA in the classical way, you will compute the covariance matrix, you do the eigenvalue decomposition, right? But if you do PCA using this probabilistic PCA way, you can learn this W not using eigenvalue decomposition, but by doing this maximization of the log likelihood. So you can do actually EM. So for factor analysis, the way you learn all of its parameters are by doing EM, right? So the same way you can do EM to get solution for PCA. So now you have 2 different ways to do PCA. One is probabilistic, and one is more sort of matrix decomposition type style approach. All right? And these are the benefits. So the question is, why would you want to do EM, right? So EM can, in some cases, when the data is very large, EM can be faster, and it can also be implemented in an online fashion, right? So because as the data comes in, you can keep recomputing your E and M. So it is more adaptive to that kind of setting, and it can also handle missing data. So if you have some missing portions in your data, let's say you get one X in which some of the variables, some of the attribute values are not there, maybe because of an error or just a recording issue, then you can still use EM there, because EM sort of works with missing data as well. Any questions? Okay, so one way to do PCA, of course, is that you do covariance matrix and eigenvalue decomposition, but that's not how typically any practical solution for PCA does give you the answers, right? So the way this, typically if you look inside any PCA, if you look up, tear open the sklearn's PCA code, you will see that they do something else, which is called SVD, singular value decomposition, right? So let me quickly talk about that. So singular value decomposition, of course, is a mathematics topic, right? And I'm assuming some of you are familiar with that, but what we are going to do is we are going to look at this mathematical technique quickly, just from the perspective of how it can help us in understanding data, okay? So it shouldn't take too long. So to start off, let's do this. Right. So we're looking at singular value decomposition, or SVD. So mathematically, SVD essentially is written like this. If you have any matrix X, okay, and X can be of any dimension, so this is our data matrix. What this decomposition says is, can I break this matrix into a product of three matrices, U times S times V transpose, okay, where S is a diagonal matrix with values, so diagonal matrix means just values along the diagonal. So let's say X is n cross D, okay. U is a orthogonal matrix, so essentially U transpose is 1. So if you, or identity, if you take any two columns of U, multiply them, you get a 1. And same thing with V. So if you do this kind of decomposition of this matrix, that's called singular value decomposition, all right? And these are called the singular values, the values that are inside S. And the values, the vectors in U are called left singular vectors, right? So this is called the left singular matrix. And this is called the right singular matrix. Now, what typically people assume is that these are ordered. So this one is the largest, this is second largest, so on. It need not be so, but just to, I mean, you can always order it afterwards, right? So assuming these are ordered, then the first left singular vector will be basically the first singular vector, and then the second singular vector, third singular vector, and so on. And same way, first right singular vector, second, and so on, right? So this is what SVD looks like mathematically. But how does it help us, right? So the first thing I want to talk about before we jump back into this is the notion of a rank. Rank of a matrix is something that I'm sure you have studied in linear algebra, right? So if I have a matrix, right? So the rank of a matrix essentially is the smallest number of columns that can be used to generate all of the columns, right? So let's say I have a matrix like this: 1, 2, 7, 3, 2, 7, 3, 2, 7, 3, right? So this is a 3 by 3 matrix. So the maximum rank that any matrix can have is the number of columns it has, right? But the rank of this matrix will be 1, right? So the rank is 1 because you can construct all of the columns using just one column, right? And the same way, so if you have 3 columns and one of them is a linear combination of the first two, so the rank will be 2 and so on, right? So that is the notion of rank, right? So how does the rank help us? The idea is that, so let's look at it more from vector spaces, right? So think of a matrix, each column in a matrix, as a basis vector that defines your coordinate space. So let's say you have a matrix which is n by d. Let's say X is n by d matrix, right? So for us in machine learning, this is a data matrix, right? Which means that it has n data elements and d attributes. In linear algebra, this essentially is a matrix which represents d basis vectors, and each one of your data point is in this d-dimensional space, right? However, if the rank of this matrix is less than D, it means that the data actually is not in a D-dimensional space. The data is actually in a reduced dimensionality space. And so let's say if rank of X is 2, what does that mean is, what that means is that there are only 2 vectors using which I can generate all of my data, which means that all of my data points lie in this 2-dimensional space, right? So it quickly sort of guides you towards the notion that this could be used for dimensionality reduction, right? So that's a notion of SVD for us. All right. So let me go back to the slides because I don't want to write it again. But this is how we define SVD, right? We assume that there is an X matrix that's decomposed or factorized as a product of 3 matrices. U will be n cross n, S will be n cross D, and V will be D cross D, right? So how this helps us is that, so of course, if I take USV, if you do SVD, right, and if you get your USV, and if you multiply them together, you will get exactly the same X back, because that's what this says, right? X is equal to USV, so USV transpose. But if I choose only a few singular values, right? So if this is called thin SVD, where instead of using all the D singular values from U, or all the N singular values, I only choose L, which is shown here, and I only choose the top L singular values in my S, and only the top L left singular right singular vectors. So each one of them will give me a smaller matrix, UL, SL, and VL transpose. If I multiply them together, I will get a matrix which will have the same dimensionality as X, right? That's easy to see because this is going to be N cross L, this is L cross L, right? So when I multiply it, gives me a N cross L matrix, and this is going to be a V is going to be D cross L, so V transpose is L cross D, right? So when I multiply N cross L with L cross D, gives me N cross D, right? So it gives me back something that's actually an approximation of your X, okay? So this is a way to compute the low rank approximation of your original data matrix. So if you have a huge data matrix, right, you do SVD on it, and I haven't told you how to do SVD, but probably, I mean, I'll tell you later. But let's say we have this, we got this, right? Now if I only choose the first L singular values and singular vectors, then I can recover my X, okay? And later I'll show you that this recovery is guaranteed to give you the minimum error among all low rank decompositions. But how does that help us? See, the way it helps us is in 2 ways. One is a little more intuitive, a little more, I mean, just hand waving. But the idea is that if you remove these low singular vectors, right, what you're kind of removing is the noise. And by recomputing your X, what you would be able to do is sort of remove the noise from your original data. So that's one thing. Another is more from the storage perspective, right? So think about this. This was your original data. That was N cross D, right? But instead of that, if I only have to store these entries, so this will be N cross L, NL, plus L. Remember, this is, even though this is L square matrix, but this is a diagonal matrix. So it's just NL plus L plus DL, right? Which will be much smaller than ND if your D is very large. So it gives you a way to compress your data and then recover your data back with minimal error. So there's a theorem. Sorry, things are out of order. There's a theorem called Eckart-Young-Minsky, or in some other order, also known as matrix approximation lemma, which says that if you decompose your matrix using SVD and reconstruct your matrix, the lower rank approximation, then the error that you get between your values, right, will be minimum among all possible low rank approximations, right? So the point is that the low rank approximation that SVD gives you a good compression. So from N cross D, you go to N cross L, and it also gives you the best possible approximation. So that is the idea, all right? So let me show you with a sort of quick demonstration. It's already open. Right. So let's say we have an image. So that's our data. Okay. So earlier we were using each image as a data point. Here I'm going to use my image as my data. So it's a n cross d image, right? So let's say I took this image from the internet, just an arch from Nevada, I suppose, and I removed the color. I just want to work with grayscale. So this is our image, right? And I convert it into a NumPy array. So this is sort of how it looks like. Now I'm going to do SVD on this, right? I'm going to use the linear algebra package within NumPy to do SVD. So what this will give me are three things. One is your left singular value matrix, singular vector matrix U, your singular values in S, and your right singular vectors, right? So just like we did it in SVD or in PCA, you can look at your singular values, and that tells you how many singular values you need to use. Okay, so for example, in this data set, it says that don't use all of your singular values, just use maybe 6 or maybe 10 or 20, right? That will be good enough. So those singular values are also useful. Okay. Now what you can do is you can compute an approximation of your image by doing this, by doing this. So instead of, actually this should be L, instead of taking your U, S, and V, just take the top L and recompute your image. And then this is how so if I just take the first singular value, right, this is how the reconstructed image looks like. Doesn't look much like your original image, but what the theorem tells you is that among all possible ways of doing a low rank approximation, this is the minimum error. So this error, the error between this and the original image, right, is 51,000. So it's just basically pixel by pixel a difference and square and sum of that, right? So that's easy. That's also known as a Frobenius norm, by the way. Now let's see if I do some other way of low rank decomposition. So another way of doing low rank decomposition is just pick one column from your data matrix and replicate it d times, right? So that new image will also have a rank of 1, right? Because you're using only one matrix, one vector to recreate your entire image, right? So I could do that, and then I can compute the error, right? Another way to do it is I can take the row means. I can take all the rows and take a mean of those, row means, and I can use that to represent my image. That's again a rank 1. Another is I can take some row and some column randomly from my image, right? Some row, some column, and I just multiply them. It will give me a matrix, right? And that also will have a rank of 1. And another is I just take column means and row means and multiply them. So these are just some heuristic ways. I just sat down and say, how many ways can I generate, take this original image and create an approximation of rank 1, right? And these are 4 ways I got them. And in each one, if you look at it, this is how the approximated image looks like, right? Nothing close to what the original image was, right? And these are the errors that you get. So this is 102, 65,000, 302, 344, right? Very high compared to if you did SVD, the error is low. So this is the sort of an empirical demonstration of that theorem, which shows that whatever you do, whatever low rank decomposition method you come up with, if you compare it to what you get from SVD, the error will always be higher than what you get from SVD, all right? So that is the idea. Now, of course, what you can do is, now this is the error that you get from SVD. So you see that SVD kind of misses a lot of part, right? Because you only looked at the first singular vector. But if you take more than one, so let's say you take 5 and recreate your image, you start seeing some correspondence to the original image. And as you keep increasing the number of singular vectors that you take, right? So basically you are traversing this in this direction, you will see that you'll start looking closer and closer and closer to the original image. So this one looks at only 50 singular vectors, right? But when you recreate the image, it looks very much similar to the original image. So this gives you a pretty good compression method, image compression method, right? So and so the size is also very easy to compute. So the size of this will be whatever number of rows times 50 plus 50 singular values plus whatever number of columns times 50. So it's linear in the size rather than quadratic, which was in the original image. All right? Any questions? Yes. Good. So very good question. So the question is, what is the relationship between this and PCA, or how are they different, right? So remember, so one way is, of course, they are the way you compute it is different, right? So in PCA, you actually first take the covariance matrix, right? And then you do an eigenvalue decomposition of that. In SVD, we do not do eigenvalue decomposition of the covariance matrix. We directly work with our original data matrix, and I'll show you how do we compute it. So that is a difference. Having said that, what my next slide was going to be was that they both are actually the same thing. Or actually, you can use SVD to compute PCA. Instead of doing eigenvalue decomposition of the of your covariance matrix, you actually do SVD of your original matrix, and that will give you the principal components. And I'll show you why and how. All right, so they are slightly different, but actually they are very related to each other. But they give you the same effect, right? So they're both giving you some kind of a lower, well, so SVD doesn't necessarily give you a low rank it doesn't give you dimensionality reduction. It gives you the compression of the data. So you have some data, it gives you a factorization of the data, and that lets you recreate the original data, but it doesn't let you map data into a low dimensional space. Singular vector? No, there is. See, the way you choose your singular vectors is by looking at the singular values, right? So the first singular vector should be the vector that has the highest singular value. You see what I mean? So that those singular values determine the order of your singular vector. So it's important. So you cannot choose any singular vector, right? So the idea behind SVD is like this. So it is more of like a data compression method than a dimensionality reduction method, but later I'll show you how it is used to do PCA. But let me just sort of give you a little more intuition behind it, right? So let's say this is my original matrix, and what we'd say is that this is represented as a product of these three matrices, right? So U, S, V transpose, right? And S is actually just a number. So what essentially happens is that if I just take the first singular value, right? So what I'm doing is I'm taking the first column and the first number here and the first row here, and then I'm multiplying them together, right? And that gives me a, so this is my X, that gives me an X hat, which is just this column times a number, the first singular value, times this. So this gives me this, right? Now I can do that for every possible vector. So I can take the second one and I can recompute the another image, which is the second singular value, singular vector times singular value times second row, right? So each corresponding triplet will give me a sort of an approximate image, and then X will be nothing but summation of all of these, right? So as you keep increasing the number of things that you will use, you will keep increasing the fidelity of your data. So, or you will keep reducing the loss of information. But what if you look at the scree plot of your singular values, they will tell you, these are the singular values which are here. They will tell you how many to use, or basically they'll inform you that beyond this you do not want to add more because they won't help you anymore, right? Okay, so now let's look at the connection between eigenvectors and singular vectors, right? And what we'll see is that they are highly related. So let's say our data matrix was X, right? So let's say X is U S V transpose. Okay. And let's say for now we are assuming that X is mean-centered, so there is no mean there. So now if I want to compute X transpose X, let's say. So what will this be? This will be U S V transpose U S V transpose, right? And now if So I can open this up and everything. So you can, I'll skip some of the steps, or we can do that. So this is V S transpose U transpose, because when you put a transpose inside, things get flipped around, right? So U S V transpose. Now we remember that by the property of SVD, U transpose, or U transpose U, is going to be a identity matrix, because that's the definition of an SVD. So but U transpose U identity is nothing but V S transpose S V transpose, right? Now these are, S is a diagonal matrix, right? Which means that so it has some values here. So if I take S transpose S, it will just be square of these values. So sigma 1 square, sigma 2 square, sigma d square, right? Because they are all diagonal matrices. So these are sigma 1, sigma 2, sigma d. So let's call this D, some matrix D. This is also a diagonal matrix in which every diagonal entry is just a square of the corresponding singular value. So let's call it V D V transpose, right? Now if I multiply X transpose X with V on this side, this will be equal to V D V transpose V, right? Now we know again by the property of singular value that V transpose V is equal to identity, because that's what we enforce, right? So which means that X transpose X times V is VD. All right. So now let's look at it a little more carefully. So this is a matrix, right? And you can see that this is sort of the covariance matrix with n. We can always put the n somewhere. This is a matrix. This is all of your right singular vectors, right? So if I take any one singular vector from here, so X transpose X, the first singular vector, the first column of this V, what we are saying is this is equal to V1 times the square of the first singular value, right? Because that's how it is written. So think of this V as just a matrix with V1, V2, and so on, and D as just a matrix of numbers. So if you write it out, this is what you'll get. Okay, which means, so, and we know that, let's say this is some matrix, right? Let's call it A. So this looks like this. Let A is equal to X transpose X, or X transpose X equal to A. So then A V1 dot is V1 dot sigma 1 square. So this is a vector, this is a vector, and this is a scalar, and this is a square matrix. Square matrix because it's X transpose X, right? So the solution for this will just be the eigenvalue decomposition of your A, right? Which means that if you think of X transpose X, so this is sort of similar to the covariance matrix of your X. Okay, that's how you compute the covariance matrix, right? Which means that if you did PCA and computed the eigenvalues, they would be same as if you did SVD and computed the singular values, singular vectors. Sorry. So what this says is that each singular, or each, these are V, right? Each right singular vector is equal to the eigenvector of X transpose X. Okay, and you can also see that each singular value is square root of the eigenvalue of X transpose X. All right, so this is the relationship between the two. So now instead of doing, if you wanted to do PCA on some data matrix X, the original approach would have been to first compute the first compute the covariance matrix, thank you, and then do the eigenvalue decomposition of that. But instead of that, what you could do is you could do SVD of X and just take the right singular vectors, all right? And you can take the square root of the singular values, or the square of the singular values, and that will give you the whole PCA essentially. You also will have to multiply with the size of the data, because this is not exactly the covariance matrix, right? Covariance matrix is 1 over n minus 1. So you'll have to account for that, but that's easy, right? So this is the relationship, right? Now the next question is, what about u? We did it for v, but what about u? And in the class notes, you will see that I do it for u as well. But the general idea is that instead of x transpose x, for relationship with u, what you do is just compute. So x is u s v transpose, just compute x transpose, and then go on from there and follow the same philosophy. And what you will see is that each left singular vector, which is in the u, right? Each left singular vector of x is equal to the eigenvector, corresponding eigenvector, of course, right, of x transpose. So just flipped. So it doesn't help us for a PCA, but these are the relationships. And the same thing with each, and the eigenvalues will be the same. So each singular value of x, or each, no, what am I saying? Yeah, value of x is equal to the square root of the eigenvalue of x transpose. But if you do x transpose or x transpose x, and you do eigenvalue decomposition of these, right, you will get different eigenvectors, but the eigenvalues will be the same. That's easy to show. All right, any questions so far? Yes. You'll have to say it again. Sorry. Okay, so the question is, I mentioned that SVD could help you remove some superfluous noise in the data, right? So the reason I said that, and I think you can show that as well, is that think about this theorem, right? The Eckert-Young-Mirsky theorem. What that says is that if I do SVD, I get a new matrix XL, right? And if I do X minus XL, that is my loss. Oh, you can't see it. Sorry. So as I said, right, there's this matrix approximation lemma which says that among all possible rank L approximations of your matrix, SVD gives you the best approximation in the sense of minimizing this norm, which is called the Frobenius norm. So Frobenius norm is nothing but, if you have a matrix, you just take each value, square it, and sum it up, and then take a square root. So that's Frobenius norm. But in terms of minimizing, SVD gives you the best. But the point I'm trying to make is that whatever is left, you can think of that as noise. That was not really useful. So going back to this example I had, right? So this was my original image. Where is it? Here, right? This is my original image. And I did SVD on it. And I did this. And let's say I take the first 50 singular values. So L is 50. So of course the error has gone down, right? So this is what you get. So comparing this with this, right? So this is my X, this is my, what do I call it, Z. So let's just plot that. X minus Z. So this is the error, right? So you can see that there's not much information in here. So what SVD has let you do is actually eliminate all of this error out just by looking at the first 50. So that's why I say that it sort of removes the noise. And the reason it helps us is that now if I want to work with this data, so instead of the original data, if I work with this data, you know that all of the dimensions that we have are important, because they all contribute to give you this. All right. So one quick, okay, I just have 1 minute. That's okay. We can stop here. Are there any other questions? So one thing I wanted to show you was to show how SVD can also be used to do something slightly different, which is matrix completion. okay? And there's one application of this in recommender system. So let's say you have some data in which you have information about some people and what things they buy, right? So something like Amazon would have, and you want to, but you do not have information for everything. So every person has not bought everything, of course. Now you want to predict what other things can I recommend to this person. That is a classic recommender system thing. But you can think of it as a matrix of completion problem. So you have some data and some things have zeros in there because somebody has never bought a certain product. Now you want to fill those out. You can do that using SVD. So let's say this is my data, right? So I have few people, 8, and these are some items that they have been buying. And let's say we are working with just a binary. So they've either bought things or not, or we don't have information. So what we do is we convert it into a like a 0-1 matrix. So there's 0 if they've never bought it and 1 if they have bought it, right? Now if I do SVD on this, right, and look at the, of course, the elbow plot of singular values, and then say, hey, you know, let me just take, I mean, I don't know how many I took.